Okay, just 1 second. So we're just going to complete the paper that we were solving yesterday. Just a second. So it's going to be this paper, March 16, question paper 221. Second. Let's just show you my. I figured out the problem. My phones are not connected. Just 1 second.
हाँ चलो ठीक है अब सही है अभी क्लियर है सही क्लियर है कैन यू हियर मी प्रॉपर्ली
Yes, sir. Yes. Yes.
अच्छा अब ठीक है So this one, starting with the first question, March 16 question paper 2 the first question is what's happening to the you're supposed to give an explanation for each of the following statements. The atomic radius across period 3 Na2Ar decreases. So what happens when you go from Na to Mg to, so you have Na and then you've got Mg, then you've got Al after that. ठीक है तो what happens when you go to the right? You've got more protons, so nuclear charge or proton numbers increase. And they have the same number of shells. Which means they're going to have the same shielding. So hence there's going to be more attraction for outer electrons. So Na has the same number of shells as Cl. Cl also has exactly the same number of shells, except that Cl has more protons, so there is going to be more attraction for electrons. So wahan pe there's going to be a lot more attraction for electrons. Then you've got the first ionization energy of sulfur is lower than that of phosphorus. So this is a dip at group 6. Why do you have a dip at group 6? Across the period, the ionization energy usually it just constantly increases. Dips at 3, 4, 5, then at 6 there's going to be a dip, and then 7 and 8. So across the period, your ionization energy graph would look something like this. So why is there a dip at group 6? What happens? So you're going to talk about sulfur. Sulfur's electronic configuration would be in its outer shell, it's going to be 3px. I mean, the 3p orbital or subshell is going to look like this for sulfur. And for phosphorus, the 3p subshell is going to be, it's going to be half filled. So यहाँ पे क्या होगा कि this is where so it's because of this reason there's going to be spin pair repulsion. It's going to be easier to remove electrons from this atom because there are two orbitals in the same there are two electrons in the same orbital, so which makes it due to repulsion it's going to be easier. So what you're going to write specifically for 2 marks is that in sulfur electron is removed. I mean, the first thing you're going to mention is removed from a paired p orbital. So the first comment that you're going to make is about the differences in the electronic configuration. While phosphorus electron is removed from an unpaired from an unpaired p orbital. And the second comment would be about the spin pair repulsion. So paired p orbitals have greater spin pair repulsion. The two electrons are going to repel each other. So hence, sulfur, it would be lower. Sulfur's electronic, removing the electron would be a lot easier in the case of a sulfur atom. So it's a typical question that comes almost in every paper. So the next one is sodium is a better electrical conductor than phosphorus. That one is easy. That sodium first thing is metallic. You can describe it as a giant. You can describe the structure. It's a giant metallic lattice. TK, you're given 4 lines, so you can give the full description. Phosphorus is, describe the structure. What's the difference in the structure? That's a simple molecular structure with covalent bonds. So why do metals conduct electricity better? Because they've got delocalized electrons. So the second comment should be about a sodium atom or the sodium lattice having these delocalized electrons in its structure. So that would be your second comment on this. Then magnesium is a better conductor than sodium. The reason is magnesium has more delocalized electrons. They're both metallic. As it forms, or you can write about its valence shell, that it has 2 valence shell electrons. So more delocalized electron, while sodium only has 1 valence shell electron. So Na at best will be able to just delocalize 1 electron. So the metallic lattice is not going to have a lot of electrons in the first place. Then you've got nitric acid reacting with Mg. So whenever a metal reacts with an acid, 2 things are going to be produced: a salt, which in this case would be magnesium and nitrate, and the other thing would be H2 gas. So metal plus acid produces salt plus H2. Or now he's decomposing the nitrate. When you decompose the nitrate, an oxide is produced, NO2 is produced, and oxygen gas is produced. The only reason is he's adding water to it is because it's aqueous. So the water vapors would also be present when you heat it. So nitrates decompose to form these 3 things. And then he's adding reagent X to form a white precipitate. So we're going to figure out what the white precipitate is. The first thing is we did write down all the formulas of A, B, C, and D. And then he's talking about E. E reacts with dilute aqueous acid to produce a gas that turns lime water milky. So E reacts with water to produce a gas that turns lime water milky. So this gas is going to be carbon dioxide gas. And the only reaction with acid that we know of that produces carbon dioxide gas is a carbonate reacting with an acid. So carbonates, they tend to react with acids to produce salt, water, and carbon dioxide. So it's going to be a carbonate reacting with an acid. So E is a carbonate. So what's happening here? You've got a magnesium nitrate, and that's turning into a carbonate, and it's insoluble as well. So it's a solid as well. So what is happening here? A nitrate. Now the only possible carbonate that's possible is it's probably going to be magnesium carbonate. And because magnesium is the only metal that's over here. I mean, there's no other metal anywhere. So magnesium nitrate would probably be turning into a carbonate, and it's obviously going to be a magnesium carbonate The substance would be magnesium carbonate because you just have Mg over here. And we figured out that it's a carbonate because carbon dioxide gas is produced when an acid reacts with it. So that happens with carbonates. So suggest the identity of the reagent X. So the question is, how do you convert magnesium nitrate to magnesium carbonate? What reagent X would you add? Now that's known as a precipitation reaction. In a precipitation reaction, you just mix two random things as long as they're soluble. For example, in this case, you've got one of them is magnesium nitrate that we're going to add to water. So in ionic precipitation, this is what happens. That if you dissolve magnesium nitrate and it's aqueous, which it is because it's very soluble, the ions would dissociate and completely mix with water. So all the ions will get scattered, and they would be floating around, lots of magnesium ions, lots of nitrate ions, all randomly floating around in water. And we need to convert it into magnesium carbonate, which is a solid. So a precipitate must be formed. Now, you need to add carbonate to it, and it could be any carbonate as long as the condition is that it's a soluble carbonate. So I can add sodium carbonate to this, Na2CO3. I could have used any carbonate as long as it's soluble. I could have even added a carbonic acid molecule as well. Anyways, if I add sodium carbonate to this, what's going to happen is that in the solution, the magnesium ions and the carbonate ions will join up. And when they join up, they form insoluble MgCO3. A precipitate of MgCO3 solid is going to be produced. Because Na2CO3 was soluble, so it dissociated into its ions. MgNO3 twice was also soluble, so it too dissociated into its ions. The ions were randomly floating around. They were randomly mixing up. Mg ions and carbonate ions, if they get together, they would form an insoluble solid, which is going to be MgCO3 solid in this case. So it could be any carbonate. So remember what ionic precipitation is. In ionic precipitation, you mix two random substances, and as long as they don't have any specific reaction. For example, if I mix NaCl with AgCl, not AgCl, it has to be a soluble. So if I mix it with AgNO3, both of them are aqueous. So the condition is that they both must be aqueous. So that means in the beaker, their ions are going to mix up. Na+1, they will dissociate, they will scatter, they'll mix up with water. Silver ions are formed, NO3 -1 ions are formed, and these ions would randomly mix and match. And if your Ag and your Cl ions, they combine. Just a second. So if your Ag and Cl ions, they combine, these two ions would form a precipitate. A solid precipitate would settle at the bottom, which would be AgCl solid. And the ions would vanish from the solution. NaNO3 would remain in the solution because even if they combine, they form something that's very, very soluble. So NaNO3 would remain aqueous. So this is what ionic precipitation is, that you mix any two random substances, as long as they don't have any typical reactions. The substances will dissociate into their ions, and the ions would randomly mix in water. And if two ions get together to form something that's insoluble, an insoluble solid would be formed. The thing with this is it doesn't always happen. And so this is what was expected of us, that magnesium nitrate we wanted it to be changed into magnesium carbonate solid. Magnesium nitrate was soluble, so the ions dissociated. I added a carbonate ion as long as it's soluble into the mixture, and the carbonate and magnesium ions, they got together to form MgCO3, which is a solid. Okay. Is this clear? Yes or no?
Yes, sir. Yes.
So now, question number 2, TK, this is your moles question. Now, in this question, he's saying that there's something called spathos. It's an iron ore that contains iron 2 carbonate. The percentage of iron 2 carbonate can be determined by titration with acidified potassium dichromate. 6, solution using a suitable indicator. So here's your iron. This is the equation. And most of this iron is actually coming from, I mean, this is spathos. It's coming from spathos. So you've got spathos over here. And the iron ions, it's got iron carbonate, and that's where your iron ions are coming from. So he's taking 5 grams of this spathos. And now remember, it's better to actually just, he takes spathos. So I'm going to just draw a rough diagram. Now spathos, remember, is FeCO3, and he's taking 5 grams of this. Now spathos is an ore. That means the amount of FeCO3 would not actually be 5 grams. It's going to be a lot lesser than 5 grams because there's going to be a lot of other stuff that would be with it. So then what he does is that he reacts it with concentrated hydrochloric acid and then filters it. So he's reacting it with HCl. So that means there's going to be a reaction, and the carbonate would react with the acid to form FeCl2 plus water plus carbon dioxide. And he filters it. So now your solution contains FeCl2. Or it contains basically Fe2 plus ions, which are all coming from spathos. And the solution is made up to 250 cm3. So he adds water, and it's now a diluted 250 cm3 solution.
Sir,
Yes,
sir, FeCl2 is insoluble.
it is soluble. Okay, so what he
So
did,
how we filter it?
the rest of the impurities get filtered out. For example, ore ke andar there is sand. So FeCl2 passes through. वो बाकी जितनी भी rocks etc. all the other impurities they get left behind. Is this point clear?
Okay.
Okay, so he's just trying to get pure FeCl2. Okay. So he's filtering out the other things. वो जो भी solids in the ore, okay, the rocks etc. all of them they're getting filtered out. So you're getting a pure solution of Fe2 plus now, and it's 250 cm3 now. He added water and made it up to 250 cm3. Now 25 cm3 sample of this was titrated. So he takes 25 cm3 sample of this, which is basically Fe2 plus. It contains Fe2 plus. Takes it into a flask and titrates it with what? He titrates it with dichromate 6, which is Cr2O72 minus. And the bottom flask contains Fe2 plus. But remember, he only takes 25 cm3 of the solution that he created, not the entire thing. Okay, so he only takes, इसको भी नीचे कर लें कि, so he only takes 25 cm3 of the original solution. Now he's saying about dichromate 6, that 25 cm3 sample required 27.3 of 0.02 mole per dm cube dichromate 6. So at this part, we know the concentration of dichromate 6, which is given, it's 0.02 mole per decimeter cube. That's provided to us. And he's also given us the volume as well, which is 27.3 cm3. So we can use that. And remember, in your theory paper, make sure you learn how to write answers properly. Make sure you write formula. I mean, show you're working properly and neatly. A lot of people are not. You have to present your whatever you're doing very clearly. I mean, clear is the better word. Not neat. If you have a bad writing, you can't really help it, but it should be clear. Everything that you do should be clear what you're doing. So even if you make some mistake, the examiner would still might give you a watermark because maybe you made a mistake on your calculator. So the examiner would still give you marks for this. So you've got 27.3 cm3. That's the volume. So concentration times volume, it's going to be 0.02 00 multiplied by 27 0.30 divided by 1000. So how many moles do we get for this?
5.46 into 10 to minus 4.
So this is going to be 5.46 times 10 raised per minus 4 moles. And I think that's an exact value. So, and be careful about the significant figures. One of these values is 4 significant figure accurate. The other value is accurate up to 3 significant figure. Make sure your answer should be accurate up to the least significant figure. So if the minimum accuracy is 3 significant figure, use 3 significant figures here. Now you found the moles of this thing, dichromate 6. We found the moles, and we are getting how many? We're getting 5.46 times 10 power minus 4. Now he's asking us to find the moles of Fe2 plus that are in the flask, and he's given us the equation. So Cr2O7 and Fe2 plus have 1:6. The ratio is 1:6. So the amount of Fe2 plus in the flask would be 6 times this. So how much do we get? And is this clear?
3.28 into 10 to minus 3.
You can clearly show everything. I says you've gotten 3.28 times 10 power minus 3 moles. In the next part, so this is the moles that you found in 25 cm³ of the sample that you're titrating. Now what you've got to do is you need to find the moles in the 250 cm³ that you made over here. So it's simple ratios. Like in 25 cm³ you got these many moles. So in the original 250 cm³, how many moles would that be? That would be just the same moles multiplied by a factor of 10. So this is in the 25 cm³ sample, you got these many. Show your working again. So in 250 cm³, you're going to have X, which is going to be just multiplied by 10 at the end. So you're going to get 3.28 times 10 power minus 2 moles if you multiply the previous moles by 10. Is this part clear? Okay, we got the moles in the 25 cm³ that we would, yes.
Shouldn't we convert the CM cube to DN cube?
In this case, if you're using ratios, it wouldn't really matter. I mean, you can do that. It's going to be this would be 0.25 and this would be 0.025, and that would turn it into DMQ. But remember, if you're just using ratios, it doesn't really matter. You'll get the same answer.
Okay, sir.
And so now use your answer to calculate the mass of iron. So we found the moles in this 250 cm³ solution, which came out to be 3.28 times 10 power minus 2 moles. Where were all these moles coming from? They were coming from spathos because you dissolved spathos. So all the iron in the solution came from spathos. So he's now asking us to find the mass of iron 2 carbonate present. So all the iron came from iron 2 carbonate when it dissolved. It's going to have the same ratio because 1 FeCO3 contains 1 Fe2 plus. So the moles of Fe and the moles of FeCO3 would be exactly the same. So we need to find the mass. To find mass, the formula is moles multiplied by MR. And we're going to use the same moles of Fe. Because remember, the moles of Fe and all these moles were coming from in the solution. They were coming when spathos had FeCO3. So the FeCO3 in spathos dissolved to form Fe2 plus ions. So it's 1:1. One molecule is going to 1 FeCO3 is going to produce exactly 1 Fe2 plus. So FeCO3 will have the same moles. It's going to be 3.28, and that's going to be times 10 power minus 2. And you multiply it by the MR, which in this case for Fe. Remember, be very careful. Use the proper data booklet values. So which is why we would have to open the data booklet just a second. So Fe is 55.8, C is 12, and O is 16. So make sure be as accurate as possible. So 55.8, that's Fe, plus that's 12 for carbon, plus it's going to be 16 times 3. What do we get for this? What's the mass?
3.79824.
So it's coming out to be 3.79824.7. So I'm going to round it off to 3.80 grams. Right? Is rounded off to 3 significant force, 3.789. So it's going to be rounded off to 3.80. So make sure you round it off to 3 significant figures. And the next part is calculate the percentage of iron 2 carbonate in this pathos. Now remember, you took a 5-gram sample, so the iron carbonate came out to be 3.80 grams. So the final percentage is
76.
But be careful that on the paper you're going to do this calculation. But remember, when you're using the calculator, don't round off values. For example, if the previous value, what was the previous value? It was 3.798824, right?
Yeah.
So it was 3.79824. So instead of, so remember, on your calculator, don't round off things. Okay? On the paper, you're going to round off things to 3 significant figures, but not on your calculator, because every step, if you start rounding things at every step, the final answer would deviate by a few percentage points. So it's going to be divided by 5, and we're going to get 75 point. It's going to become 76.0% anyways in this particular case. If you round it off to 3 significant figures, like if I round off the third one, like I haven't multiplied this by 100. So if I round off the third one, there's a 6 after that, so it's going to round up upwards. So it's going to become 76.0%. And that's going to be our answer in this case. But make sure when you're writing stuff on your paper, that has to be you should be using the appropriate significant figures. But don't round off values on your calculator, no matter what. And also remember, the rule for significant figures is that your answer is always accurate up till the least significant figure value that you're using. So if one value is 4 significant figure accurate, the other one is 3 significant figure accurate, then your final answers cannot have an accuracy greater than 3 significant figures. And so now next one is, he's saying a standard solution of iron 3 ions is reacted with tin 2 chloride. So Fe3 plus ions, it's reacted with tin 2 plus, and it forms tin 4 plus and iron 2 plus. So that's the equation. And he's specifically asking for the ionic equation. So we're going to give him the ionic equation, which is Fe3 plus reacting with tin 2 plus, and it's forming tin 4 plus and Fe2 plus. So now, can anyone tell me what's so this is the ionic equation, but can anyone spot what's wrong with this equation at the moment? What's wrong with this equation?
Balancing.
Okay, so and atom wise it's already balanced, but the thing is,
Charge wise.
it has to be balanced charge wise or electron wise. The number of electrons gained and lost must be equal. Fe3 plus goes from 3 plus to 2 plus, so that means it gains how many electrons? 1 electrons. I mean, one, or the shortcut is you just balance the charge. But the thing with charge wise balancing is that you can't always rely on that. Which is why I always go for electrons. Like, just make the number of electrons gained and lost equal. So Fe3 plus is gaining 1 electron, goes to Fe2 plus. Tin 2 plus loses 2 electrons. So you just multiply Fe by 2 so that the number of electrons gained and lost are equal. They've got to be equal. So Fe is going to be multiplied by 2 in this case. So always try and use this habit of figuring out who's gaining electrons, getting reduced, who's losing electrons and getting oxidized. The number of electrons lost and the number of electrons gained, they must be equal, which is why I multiplied Fe by 2. Is this clear?
Yes, sir.
So if you've got tin 2 chloride can be removed by reaction with HgCl2, a white precipitate of Hg2Cl2 is produced. Complete the equation for this reaction. So I think everything is given except for tin 2 chloride. So we can add tin chloride. It's going to be SnCl2 because it's 2 plus and Cl is -1. And he's already told us the state of tin 2 chloride, which I think it's given over here. It's aqueous. So that is already aqueous. The state is already mentioned. Tin 4 chloride, the state is also given. That's aqueous as well. It's written over here. So that's aqueous. And he already said that Hg2Cl2 is a precipitate. That means it's a solid. So most of the things were already mentioned above. I mean, all of them were actually mentioned above, even the formula. So you just had to write down the states by copying from above. So now next question is, you're supposed to draw the dot and cross diagram to represent the bonding in a molecule of ammonia and state the shape of the molecule. So the dot and cross diagram is easy. There's an N and there are 3 H atoms. Each one of them is sharing 1 electron each. And N over here has a lone pair. The shape of the molecule is derived from a tetrahedral shape. I mean, this is not tetrahedral, but it is derived from a tetrahedral shape that it's got 4 pairs of electrons, 4 bonded pair, 3 are bonded, and 1 of them is a lone pair. The top is missing. There's no atom attached on the top. So we're going to get rid of the top. So it's a tetrahedral with the top missing. Tetrahedral atoms, they have an angle of, tetrahedral molecules have an angle of 109.5, but because of the extra repulsion of the lone pair, the angle over here becomes 107. So this one is known as a trigonal pyramidal shape. That is the shape of this molecule. The next part is you're being asked to draw he's saying draw the bonding between carbon atoms and nitrogen atoms consists of 1 sigma. So you're supposed to just sketch the shape of the sigma and pi bonds. Can anyone tell me what type of hybridization is carbon undergoing in this case?
sp3.
When carbon is bonded to just 2 atoms. Let's remember this thing about carbon. I'm going to write it here. Carbon is going to be sp3 when it's bonded to 4 atoms, and it's going to be tetrahedral. Carbon, remember, has 4 electrons. So 1 electron gets pulled by all 4 electrons get pulled in different directions. So that is sp3. What happens is that the electron densities, they get pulled in, the electrons over here, they get pulled in different directions. And the angle is 109.5. What is sp3? sp3 is carbon originally had 4 electrons, but they were in different orbitals. Originally, carbon had, the outer shell was 2s1, 2px1, 2py1, and 2pz1. That was the outer electronic configuration of a carbon atom. But now what happened is that the electrons got stretched in different directions. They got pulled in different directions. And which is why their shapes have changed. They're no longer spherical. The electron is no longer occupying a spherical orbital, or it's no longer occupying a dumbbell-shaped px orbital or a py or a pz. The electrons now exist in different places around the nucleus with completely different shapes. So the name of the shape of the orbital has now changed. The electrons are still the same. So these are known as sp3 hybrid orbitals. So it's the same electrons, except that the region that they occupy is now different compared to what they what the electrons occupied when it was just a carbon atom. Is this clear?
Yes.
Okay. So that, remember, is sp3 hybridization. So carbon, whenever it's bonded to 4 atoms, whenever it's tetrahedral, and the angles are 109.5, it is sp3. This one is sp. sp is when carbon is only bonded to just 2 atoms. So you have an H, you have an N. Now in this case, what happens is this is how the carbon would look like. Remember, carbon has 4 electrons. So carbon's got 4 electrons. 1 electron gets attracted by one of the nitrogen atom, bonds with it. The other electron gets attracted to the other atom, which is hydrogen in this case, and bonds with it. So carbon now has 2 orbitals that are not bonding yet. So it's got 2 orbitals. One of them would be on the y-axis. It's going to be a p orbital. And the other one would be on the z-axis. So that's going to be our z orbital. So this is what, so this is what a carbon atom would look like. Like out of the 4 electrons, 2 of the electrons got pulled in different directions. And let me just, so out of 1 second. This one. So the thing I was explaining was that out of the 4 electrons, 2 of the electrons got pulled in different directions. And 2 of the orbitals that remain completely unchanged. Is this part clear?
Yes, sir.
But what would these 2 extra orbitals do? They would form pi bonds, because nitrogen also has orbitals that are not completely full. Nitrogen has 3 orbitals that need electrons. So there's a p orbital in nitrogen, and nitrogen also has a pz orbital, which is lying on the z-axis. So when orbitals become parallel to each other, they start to form pi bonds. So it's going to be something like this. It's going to be the green ones overlapping. So they would overlap above. And behind the atoms. And the blue ones would also start to overlap. So the blue ones, they're also in parallel, and they would start to overlap above and also at the bottom as well. So they're going to overlap above and below, and there's going to be an overlapping that would be behind this as well. So there's overlapping happening behind this as well. So it's going to be 2 pi bonds. There's going to be 2 sigma bonds. Those were the first bonds that were formed. So listen carefully. It's going to be sp hybridization. Carbon forms a sigma bond with an N atom, a sigma bond with an H atom. 1 electron gets pulled in this direction, 1 electron gets pulled in this direction. And out of the 4 orbitals, 2 of the orbitals, they're going to change shape, 2 of them. And they would be called your sp hybrid orbitals. I mean, these ones would be called your sp. because the shape is now totally different. They would be called your sp hybrid orbitals. The other two, they would maintain this shape. They would end up forming pi bonds. One would overlap above and below. The other one would overlap behind this and in front of this. So is this clear?
Yes, sir.
Achha, so you have to draw this, but remember you can't draw this three-dimensional diagram. So they're just asking you to draw one sigma bond. So that's what you're going to do. What you're going to simply do is, you can draw, he's saying sketch the shape of a sigma bond and one of the pi bonds. So just sketch one of them. Sigma bond, the electron density is right in the middle of the two nuclei. So you can show the H atom and its nucleus. You can show the C atom and its nucleus. And the electron density and the overlapping would happen right in the middle. So you can kind of shade it and say that the electrons are right in the middle. That's your sigma bond. And you can show the overlapping of the electrons with the N atom as well. And if you want to show the pi bonds, just show one of them. Like there's N, there's going to be an overlapping above and below. So just show one of the pi bonds. Okay. So that's what you're going to do in this case. Now, the next, and most questions would be just simple. You just have to draw a pi bond. Pi bond is when orbitals are parallel to each other and they overlap. Sigma bonds is an end-to-end overlapping. That's it. And let me just check what kind of drawings were they expecting. In this case, it's just quickly opening the marking scheme to just confirm. So March 16. So this is what they were expecting for a sigma bond and above and below for a pi bond. So you'll probably get marks for both of them. You just have to show the electron density is in the middle. And over here, the electron density is above and below. So you're going to get marks for both. Just one second. So just showing the electron density is in the middle and over here, the electron density is above. And you just have to probably tell them that this was a pi bond and this is your sigma bond. Now, next one is, so they were just looking for one sigma and one pi bond. Next one is what is meant by the term dynamic equilibrium. So it's the rate of forward reaction becoming equal to the rate of backward reaction in a reversible reaction. The next part is state and explain how the amounts of chemicals present in the equilibrium mixture will change when the pressure is increased. Can anyone quickly tell me what happens when pressure increases? Which side is favored?
Equilibrium shifts from more number of moles to less number of moles.
Okay. And just not moles, it's moles of gas. Okay. When it comes to pressure, gases are the only things that are compressible. So if your equilibrium had solids or aqueous or any other state, then pressure would have absolutely no effect. तो उसके अंदर इसका ख्याल रखना है कि increased pressure, the less gas mole side is favored. So now the only problem with this is, I think he's talking about this reaction over here. So which side is less gas? This side has clearly more gas moles. So there's clearly more gas here. Less gas mole side is favored. So it's going to be more products in this particular case. So there's going to be a lot more products. So you're going to write that forward reaction is favored, or you can talk about equilibrium shifting to the right. So there's going to be more products and less reactants, because there was a specific comment that was, yes.
It's actually, the reactant side has less moles than the product side. product side has 4
हाँ
moles
ठीक है
and reactant side
नहीं
has
I didn't
3.5.
actually I didn't see 3. So there are 4 moles, and over here you have what 1 2 and 3.5. ठीक है. So it's going to be the opposite. This is the less gas mole side. So the equilibrium is going to shift backwards, okay? So it's ulta kar lo, okay, it's going to less gas mole side favored. So backward is the one that's going to be favored. And more reactants. And you're going to have less products. I said now you've got what you have to do is sketch a Boltzmann distribution and diagram to explain how the platinum catalyst increases the rate of the reaction. So it's Boltzmann distribution is a skewed representation, which kind of looks like this. So that is what a Boltzmann distribution is. And it shows the distribution of energies of the particles. For example, these are your high energy particles. So the number of particles are fewer. These are your low energy particles, and the number of particles are fewer as well. The peak is where you have the average energy. So if your room is at, let's say, room temperature, then most of the particles would have energies or kinetic energies that would correspond to room temperature. But they wouldn't have exactly the same energy. Some of the molecules might have very high energy, some of the molecules might have very low energy, but most of them would have energies that would be very close to the average energy of the container. So most particles are going to be present at average energy, fewer high energy molecules and fewer low energy molecules. So how could you show a catalyst? Now catalyst, somewhere over here, there's a point called the activation energy. Particles beyond that point have energies that are greater than the activation energy. So they're able to collide successfully. So they're going to have effective collisions. Their energy is greater than the activation energy. So effective collisions means successful collisions. The rest of the particles are low energy. I mean, they have energies that are lesser than the activation energy. So the rest of the particles are probably not going to be able to react successfully. So what happens if you add a platinum catalyst? When you add a platinum catalyst, what you're basically doing is you're decreasing the activation energy. So now all of a sudden, you've got even more effective collisions taking place because now you have particles. This is the activation energy of the catalyzed reaction. So those particles were already high energy particles, but you've got additional high energy particles that have energy now that is greater than the activation energy. So even more successful collisions are going to be taking place now. So this is what you have to explain in these 3 words. The first thing is you're going to show the graph, you're going to get marks for that. And then you're going to label these 2 points specifically. I mean, forget this thing. And after that, what you would state is that catalyst decreases. I mean, you can just write one statement because most of the things are quite clear from the graph. So catalyst decreases activation energy. So more particles will have energies greater than EA, and the activation energy due to catalyst, which is going to be a lower activation energy. So more effective collisions would take place. Is this clear?
Yes, sir. Sir, shouldn't we draw like another curve as well for the catalyst one? Even though we have marked the axis, but like.
No, but it's
wouldn't it
just
be
going to,
better?
there's just going to be one curve. Okay, remember
Oh,
the
yes.
curve would, the curve would only change if you change temperature.
Yeah, yeah.
ठीक
Okay, I know.
ठीक है तो by adding catalyst the curve doesn't change, the distribution of energies is the same except that the activation energy is lower now. ठीक है, so there's just going to be this extra line which you're going to
Okay.
call the catalyzed reaction. ठीक है.
Okay.
As a next one, option D, you've got this is hydrogens. This is nucleophilic addition. ठीक है, so this is all aldehydes, ketones, carbonyl groups. They undergo this reaction. What happens is that this carbon has a partial positive charge. The oxygen has a partial negative charge. The CN, remember the lone pair is on C. ठीक है, make sure. So the lone pairs will get attracted to the positive carbon and the electrons over here are going to get, they'll be repelled. So Cn minus 1 will be attracted very strongly to the positive carbon and the O is going to get repelled. And in the next step, this is going to be formed, that the middle carbon atom would now be bonded to Cn at the bottom. And remember, C is the one that's going to bond. And the O at the top would become, it would lose its double bond because the double bond pi electron cloud got repelled upwards. So the electrons are now sitting at the top and it has a negative charge. In the next step, H plus 1 from HCN is going to come in and complete the structure. So it's going to be CH3. This is going to be CH3 as well. At the bottom, there's going to be CN. This is known as a cyanohydrate as well as CN, both of them. Okay, so we are done with this question. Now, and the last question, this one. So we've got question number 4. He's saying give the molecular formula of compound G. That's easy. It's like how many carbons? That's 1, 2 over here, and so that's C4. And how many hydrogens? That's 3, 3. That's 6. Plus there are 4 of them, so that's 10. C4H10. And empirical formula for this thing. So you have to calculate the empirical formula. That would be how many carbons? That's 3, 4, 5, 6, and 7 and 8. So I think there are 8 carbons. Hydrogens, that's 9 plus 2, that's 11, and 12 and 6. That's 18, I think. So the empirical formula in this case would be what? C4, H9, I think, divided by 2, divided by 2. And draw the skeletal formula of this. When you draw the skeletal formula, you only show the carbon atoms in any functional group. So you just have to show these 4 carbon atoms. That's about it. So we're going to start with the first carbon atom. That's the second one. That's the third one. So this is this part. 1, 2, 3. And the middle one, there's another carbon atom. So draw that. And in the last one, there's another carbon atom. So draw that. Who has the OH? This one has the OH, the second from the right. So that's the skeletal formula for this particular compound. You be clear?
Yes, sir.
So that's the skeletal formula. So we've drawn the skeletal formula and write the equation for the complete combustion. You can pretty much do that. Now, fossil fuels are also contaminated with sulfur. State and explain why supplies of fossil fuels pose a problem. So you're going to describe the whole acid rain thing. Okay. I think no detail would be needed. It's just that you can talk about sulfur dioxide being produced, and that would mix with, not that would mix. You don't have to write the whole thing. What you can just state is which produces acid rain. Acid rain. So fuels containing sulfur. And he specifically, so you don't have to write the whole chemistry of the thing, like SO2 turns into SO3, then SO3 reacts with water to form H2SO4. So, I don't think the chemistry is needed over here. Is what problem would it pose to the environment? That is, soils can become acidic, soil and water bodies. That's the main problem that they cause. They're going to turn acidic. So that's pretty much it. That is what happens. So, and I think we are almost done. Okay, that's the last part. We did the previous one yesterday. So now this one is about intermolecular forces. We were doing intermolecular forces in the class as well. So he wants us to comment on the boiling points. Like so lowest, I mean that's very low. These two are kind of similar. So let's go back and have a look at these three compounds. So where did our compounds go? Just a second. Not these three compounds. So first one, let's comment on this one. Can anyone tell me why is this having the lowest? I think it was around 0 degrees centigrade. Why is it?
sir,
Why is this?
basically-
Yes. Yes.
Basically because like carbon and hydrogen have almost the same electronegativity, so weak intermolecular forces. And
But what would that weak intermolecular forces be
the
called?
London dispersion forces or van der Waals forces,
Okay.
and they are the induced dipole forces, so very weak attraction.
So I think that would be enough. It only has van der Waals forces, and van der Waals forces are weak. Or you can just talk about van der Waals forces are weak intermolecular forces. So the second question is, why is this a lot higher than that? I think it was around 90 degrees centigrade. So what intermolecular force would that have?
Sir, it's basically because like there are more number of carbon and hydrogen atoms, maybe that's why. And so like much stronger van der Waals forces.
So it's a bigger molecule and it has more electrons. So it's got more electrons. So there's going to be more instantaneous or temporary dipole induced dipole and more van der Waals forces. The bigger the molecule, the more the surface area of the molecule. So more electrons, more van der Waals forces. Or you can talk about temporary dipole induced dipoles. There's going to be more temporary dipole. I'm just going to write TDID for that. I mean, in the paper, you would have to write the whole thing. So more TDID, which leads to hence more van der Waals forces. So remember, bigger molecules, van der Waals forces, they increase with size. So the bigger the molecule, the more the van der Waals forces. What about the last one? That's the highest one. Why is this having the highest boiling point? I mean, I think it was around 110.
Sir, because hydrogen bonding, hydrogen bonded with the O, making the OH, and
so
polarity.
So you can just talk about hydrogen bonds because it is obviously a very strong dipole. The oxygen is very negative, the H is extremely positive. So the attraction with other molecules is going to be very strong. So it's going to have hydrogen bonds, and hydrogen bonds are really strong. Okay, so you're going to comment on the strength. So hydrogen bonds are very strong intermolecular forces. That's it. Or have very strong intermolecular forces. The hydrogen bonds are, I mean, they themselves are the intermolecular force. So these three comments, remember, most of the time it's not, you don't have to explain how those intermolecular forces were formed. And I have the market scheme as well. We can see if we have missed anything in that case. It's just the general things. It's got more van der Waals forces. We did talk about that because it has more electrons. We did talk about that. And the last one has hydrogen bonds, which is stronger. Or more energy or greater force of attraction. So we did talk about hydrogen bonds being very, very strong as well. So that's the last one. Compound, let's I think compound J can be produced from 2-chloro-3-methyl butane. So again, what's J? J is this one. So he's saying it can be produced from 2-chloro 3-methyl butane. So let's first find out what 2-chloro 3-methyl butane is. So it's butane, 4 carbon atoms, and I think it's 2-chloro and 3-methyl. So it's kind of the same molecule. It's exactly the same molecule. Like 4 carbon atoms in a row. So they've 4 carbon atoms in a row over here as well. And on the second carbon atom from the right, there's a methyl, which is here. And on the next one, there's a Cl over here. Over there, there's an OH. So all you have to do is you have to get rid of the halogenoalkane and put an OH in its place. That's a nucleophilic substitution reaction. This is a polar bond. You can bring in an OH -1, and the carbon will attract the OH -1, and the Cl will get knocked out. That's a nucleophilic substitution reaction that requires NaOH aqueous and reflux. TK, is this clear?
Sir, what did you say after NaOH aqueous?
And reflux. Heat
Yeah,
with
sir.
reflux.
Okay. Yes, sir.
TK.
Okay.
Remember, halogenoalkanes have 3 nucleophilic substitution reactions. One is with OH -1, which they're called SN1 and SN2 mechanisms. The other one is with CN -1. And then there's another one with NH3. So with NaOH, it's going to be aqueous and reflux. So that's about it. So here, let's, I'll tell you a time of the next session that's going to be within the week. We'll do another past paper in that one, TK. So we'll continue
Okay,
next
sir.
time.
Allah Hafiz.
Okay. Take care, Allah Hafiz.
Allah Hafiz.
Hafiz.